something, I don't remember what. Who was it? I think it was some sport show or something, and I want to say it was Scottie Pippen, played for the Bulls back in the 80s, 90s, I think 80s. He said something to the effect, and I'm sure you've heard this before, that if you're not failing, you're not trying. You have to try it. You have to try it something, right? And if you're not failing, then you're not trying hard enough. I want to say that's what happened on this first quiz, that you're trying and you failed or something like that. But class average was a 50. That's a little lower than I was hoping to see. But it was the first quiz. You kind of got a little bit of a flavor for the types of quizzes that I will expect, for you to be able to come in and do. And I will always drop at least one quiz. I'm hoping to have at least 8 to 10 quizzes. So if we get up to about 8 or 10, I'll drop 2 quizzes. So you don't have to look at this as being like, oh my, it's over now, right? But if you didn't do well, you want to try and make adjustments. There's a famous quote by Albert Einstein that goes, Albert Einstein defines insanity to be doing the same thing over and over and expecting a different result. So if you are going to, if you continue to study the same way or not study the same way, whatever it is, if you don't change it, you can't expect to change in anything else. So, make adjustments. I know I've met with some of you and I've talked about maybe trying to form study groups. So, I can't force you all to be, hey, you want to study outside of class, but I encourage you to take this opportunity to, exchange phone numbers, something, so that you can get together with each other. I think working in groups is a really good thing, but again, I can't force you to do it. So, and some people don't play well with others. So, right? Yeah. Okay. All right, so let's move on. We're going to start 1.5. Were there any questions over anything before I begin this? No? Okay, we're starting 1.5. So we did 1.6 last class. We're going backwards in the book, and I told you I skipped 1.5 because I think that, this, as you see when we do it, this kind of doesn't fit right in the middle of 2 sections that have to do with limits. So now we talk about this concept of continuity. All right, so this is a word I'm sure you've heard sometime in your life, but you've never thought of it as being what it's going to be in here. All right, continuity. The definition of continuity is a very, very straightforward statement. All right, but understanding what it says or what it means is a little bit challenging. So it says here, a function f is said to be continuous at a point x equals a if the limit as x approaches a of the function equals f of a. Now, what the heck does that mean? All right, so I'm going to try and explain this with pictures. So let's take a look at this function. And let's look at what's happening at 2. All right, at x equals 2. First of all, what is f of 2? What is f of 2? If I ask you to plug 2 into this function, what's the value you get out? Undefined, right? At 2, you have a hole. So the function is undefined at 2. Now, does the limit exist as you approach 2? Yes, because from the left, your function is approaching a value. From the right, your function is approaching the same value. That value appears to be about 8, doesn't it? So what we could say for this is that f of 2 is undefined, right? Undefined. And the limit as x approaches 2 of this function you just said is what? Is 8. Do we all agree with that and understand that? Okay, the definition of continuity says this. For f to be continuous at, in this particular case, x equals 2, then here's the definition. The limit as x approaches 2 of the function must be equal to f of 2. So let me scroll back up so you can see the definition again. The definition says, for a function to be continuous at a point x equals a, the limit as we approach a of the function must be equal to the function's value at a. So that's what I've written here. In order for f to be continuous at 2, the limit as we approach 2 of the function must be equal to the function's value at 2. Now, is this true in this case? Is the function's limit equal to the function's value? Are those the same? Are they? Is this limit, which is 8, equal to that? 8 is not undefined, right? These two are not the same. Do you all see that? This f of 2 is this side of the equation. This limit is that limit is that side of the equation. In order for us to say it's continuous at 2, we would need both of those to be equal to one another. And since 8 does not equal undefined, this function would not be continuous at 2. So the answer to this question is no. Right? No, it is not continuous at 2. So what about another example? Let's look at this one. Slightly different, right? Slightly different. Let me ask you now, what is f of 2 here? What does it appear f of 2 is? It looks like it's 6, right? We plug in 2, looks like we get 6. So f of 2 is defined this time, right? It's 6. What's the limit as we approach 2? So from both sides, right? It's 8 still, right? Now, for the function to be continuous at 2, we would need the limit to be equal to the function's value there. Are these two the same? They are not the same. Therefore, this function is still not continuous at 2. Make sense? So what would we need, like geometrically, what would I need to do to make this thing continuous at 2? Okay, say it again, like some.
Well, the plot that's on 6 should be on the 8.
Yeah, I need to move this dot up to there. If I move this dot up to there, then everything will work, won't it? So let me look at that, like that. Now, what's f of 2? 8. What's the limit as we approach 2? Well, it happens to be going to the same place, 8. These two are now equal. That means this is satisfied, right? Which means this function is continuous at 2. Yes?
What about x as it approaches 2? That doesn't have to be, like it doesn't have to be equal to 8. It doesn't have to be 8.
What does not have to be 8? This right here?
X as it approaches 2.
This is 8 though. This whole, this whole side is 8, right? That's what you just said it is. Right? And then this side, right, in this problem is 8. And those are equal, right? So this idea of continuity comes from the idea that if I go back up to the first example I showed you, if I'm trying to draw this, right? If I'm trying to draw this with my pencil, then when I'm going towards 2, do I have to pick my pencil up or not? Right? In this case, I do, right? So I'm drawing, I have to pick my pencil up to go over the hole, and then I continue. That is not continuous because I had to pick my pencil up, right? The second example, same thing happens. This one, if I'm drawing it, right, towards 2, I'm drawing, I have to pick up my pencil, draw a dot, come back, and then continue. Not a continuous motion, right? But in the last example, the one that was continuous at 2, I can draw this. I don't need to draw a dot. My pen's already there, right? And I just continue through. Oh, what did I do? I continued through, right? Continuous. That's the idea of continuity. Does it make sense visually? Now, algebraically, though, this is what we have to have happen. This must be true in order for us to say a function is continuous at a single point. All right. So this is what I say here. Basically, we can see that the idea is that, can we draw our graph without picking up our pencil? All right. How about discontinuity? This idea of discontinuity. So if a function f is not continuous at a point, then we will say it is discontinuous at the point. So in the first two pictures I gave you, right, both of these pictures, right, or let's just do that one, that function is discontinuous at 2. Would you agree? Yes. Now, is it continuous at 3? Is this function continuous at 3? Yes, because if I go up here, it appears there's a dot there, right? So it appears at 3 that I would come in from the left, come in from the right to the same place, and I would have a nice continuous stroke as I drew that. So this function appears to actually be continuous everywhere that it's drawn except 2, right? So I have a single discontinuity at x equals 2. Discontinuity at x equals 2. No discontinuities. Continuous everywhere, right? You pick any value of x, and that function can be drawn nice and smoothly. There are 3 basic types of discontinuities. Okay? There's 3 types of issues that we could have that would create a discontinuity. And here they are. A jump discontinuity, an infinite discontinuity, and what we call a removable discontinuity. Those are the 3 types we can have, and here's a picture of each one. A jump discontinuity. Look at 2. What's f of 2 here? It is defined to be what?
8.
It's 8, right? Because I have a solid dot right here. So at 2, I'm 8, right? Now, what's the limit as x approaches 2 on this function? So I'm approaching 2 from which side? Both sides. Does this limit exist? It does not exist, right? From the left, it's what? 8. From the right, it's, I don't know, 5 or something. It's not 8, though, right? So this limit does not exist. In order for this function to be continuous at 2, these 2 have to be equal, right? And it's impossible for does not exist to be equal to 8. So I have a discontinuity at 2, but it's a jump discontinuity. And it's called a jump because there's actually a break in your graph. And if you were to draw this, you would actually have to physically pick up your pencil, jump to the next piece, and draw, right? So that's a jump discontinuity. That's the first type. The second type of discontinuity is an infinite discontinuity. So look at this function. What is f of 2? And in all of these examples that I put up here, I'm using x equals 2. I could have used some other value. I had to pick something. So I'm going with 2 on all these examples. What's f of 2 here? What does it appear to be? 5? Y'all agree? Okay. What is the limit as x approaches 2 from both sides of this function? So as we come into 2 from the left, we're headed up to infinity. From the right, we're headed up to infinity. So this limit does exist, right? It's infinity. But these 2 are not the same, right? 5 and infinity are not the same thing. So it's impossible for this to be continuous there if these aren't equal. So we have a discontinuity at 2, but this is called an infinite discontinuity because the function is becoming infinite near 2. Does that make sense? All right, and then the last one is what we call a removable discontinuity. And this is actually the type of discontinuity that I started this whole idea with. This right here, we already said is not continuous, right? At 2, because there's a hole. Y'all agree with that? They call it removable because it would be very easy for us to remove the problem. In order for us to remove the problem, all we'd have to do is fill in that dot, right? If I just simply came in here and filled that in, I will have removed the discontinuity, right? If you look back at the previous 2, there's no way for me to easily make this thing continuous. I'd have to completely change the shape of the graph to make this thing continuous, right? And same with this one. I can't remove that easily because there's a jump. So I'm either going to have to like bend this side down or move this side up or bring them together. And that's a lot of changing of the function to do that. Whereas the last example, very easy for me to remove the discontinuity. All I have to do, well, I don't show it here, is fill in the point, right? So you have jumps, infinite, or wholes. Those are the three types of discontinuities. Does that seem pretty straightforward? No questions? Okay. Now, right when we start getting comfortable with this, we want to define two new types of continuity. And that is what's called left continuity and right continuity. And these are two separate ideas. So let's look at the definition of left continuity. A function f is said to be continuous from the left at x equals a if the limit as x approaches a, there's a little negative sign there, don't know if you can see that, but if the limit from the left side of the function equals f of a. So this definition is a weaker condition than what we had before. It's saying that only one side of the limit has to exist for you to call it left continuous. And right continuity is the other way. Right continuity means that the limit from the right has to exist and be equal to this. So let me show you this in pictures. This function at 2 is left continuous. Now the reason why is because as we come in from the left, our function is headed somewhere, isn't it? Headed to where? 8. But then when we get to 2, it's actually 8, right? So it's nice and smooth. We can stop, boom, right there. Okay? So this is left continuous. This is not right continuous at 2, because even though we are going somewhere, right, it's not headed to the function's value, which is up here. So no right continuity, but left continuity here. That would be right continuity at 2. Continuous from the right, but not continuous from the left. Do y'all see the distinction? All right. Continuity on an interval. So a function is said to be continuous on an interval. Everything I've talked about before this, we've talked about continuity at a point, only at a single point. But now we want to talk about a function being continuous on an entire interval. A function is said to be continuous on an interval if it is continuous at every point in the interval. Every single point in the interval, it's continuous. And at the left endpoint, the function needs to be right continuous, and at the right endpoint, the function needs to be left continuous. What? Okay, so just look at this. Would you agree that between 1 and 3, anywhere in here, I am continuous at every single point? Yes? No jumps, no breaks, everything's nice and smooth, draw it. Now, when I get to this point 1, I don't have a graph over here, right? So I can't talk about continuity because continuity requires coming in from both sides, right? But I can talk about right continuity. From this side, approaching 1 from the right, it's continuous. And then when I get to this endpoint 3, the limit from the left exists, right? And it's left continuous. So to be continuous on a closed interval 1, 3, if I'm just looking between 1 and 3, this function would be continuous on the entire interval. I guess what I'm hoping you see here is that when you're on an interval, you only have to worry about right continuity on the left side, and you only have to worry about left continuity on the right side, all right? And it still makes sense for us to talk about continuity. Okay? Now a couple of theorems. Let's say that we start off with two functions, right? Let's say I give you two functions, f and g. And I ask you to either add them together or subtract them. So maybe I give you like the sine function, and I give you like a parabola, x squared. And I ask you to add them together. This theorem says that as long as the two functions you start with are continuous, that when you add them together or subtract them, you still have a continuous function. So adding and subtracting continuous functions, or the sum of two continuous functions, is still continuous. And I might be able to show this to you with an example. Maybe. Yeah, that's slow. Let's go. Hurry up. Okay, so I'm going to take, would you all agree that sine of x is continuous?
Yes.
I mean, just look at sine. I mean, from what we know about sine, you can draw it without picking up your pencil. No jumps, no breaks. everything's good, right? Let me take to that and let's add to that the cosine function, which is also continuous, right? So let's do cosine x. And if you add the two together, lo and behold, you have a new function. Here it is. And guess what? It's continuous. As long as they start with two continuous functions, adding and subtracting them, still continuous. All right? But we can't just assume that. That's a theorem. It's true. It can be proven. We don't have to prove it, but we can trust it. The next little idea here is that if we start with a continuous function and we multiply it by a number, it's still continuous. So I'll show you a picture of that. Let's say we take, let's get the sine function again, right? If I multiply it by a constant, let's say -3, right? So I put -3 sine x, I'm still continuous. There's nothing I can do by multiplying by a number that's going to change the continuity of a function. Multiplying two continuous functions results in a continuous function. So that means if I take sine x and I multiply times cosine x, is it having trouble? It's having trouble. Let me see. There we go. I think that did it. Let me multiply that by 2. That doesn't change it. So there we go. The product of 2. Let me do a third function. Let's multiply this by, y'all remember in college algebra, e to the x, right? E to the x is like this thing, nice and smooth and continuous, right? So let me multiply this times e to the x. There you go. This function, although ugly, wow. Oh, okay. Yeah. All right. Let's see. 0.0001. There we go. Oh, whatever. It's continuous, all right? You can draw it without picking up your pencil. And then finally, if we take two functions and create a quotient out of them, then the result should be continuous. Except at possibly where the function on the bottom, g, might be 0. So think about it this way. If I take sine and divide by cosine, each of those are continuous, right? Sine is continuous everywhere. Cosine is continuous everywhere. When I divide them, I am not going to get a continuous function. Watch. Sine x divided by cosine x. Yeah, that's what we should expect. It's actually, it's pretty much tangent x, right? So what you have happening here are a bunch of asymptotes, right? So if I try and draw this without picking my pencil, I can't do it. I've got to draw that, and then I've got to come back over here, pick up my pencil and draw this one, right? So I don't have a continuous function. But the theorem that I just put up here says, you have to read it carefully, the quotient of two continuous functions is continuous if the denominator isn't 0. So anywhere where the denominator might be 0, yes, you will have a problem. So if we go back and look at that graph, I want you to notice that if I just confine myself to looking in between here's the vertical asymptote here, and then there's another vertical asymptote right in here. If I just look inside here, this red function is continuous. Okay, it's continuous. It only has a problem at the asymptote. That's the only place it's not continuous. And the asymptote occurs when the denominator was 0. So, all right, I hope that makes sense. Questions? All right. So you might be asking yourself, well, which functions are continuous? I already said sine and cosine were, right? E to the x, and I didn't try and convince you of that. I just told you, and I think we all agreed when you draw them, you don't have to pick up your pencil, right? But which functions are continuous? Okay, all polynomial functions. This is back in college algebra. These are the ones that look like roller coasters, right? Those types of functions, polynomials. All of them are continuous everywhere. is when you graph them, parabolas, third degree polynomials, when you graph them, you can draw them without picking up your pencil the entire time, right? So all polynomial functions are continuous everywhere. Okay, rational functions are continuous on their implied domains. So let me explain this one. I'm going to go to a picture again. I'm going to type a rational function in here. X minus 2 over x squared minus 9. Okay, this is a rational function. That's something you would have graphed in college algebra. Now, this is not a continuous function everywhere, right? Because you've got asymptotes again, don't you?
Yes.
But what we're saying is that on their implied domains, they are continuous. So the only place where we'd ever have problems with this function is where? We look at this. Where's the only place we're going to have an issue? 3 and negative 3, right? So if I go to 3, negative 3, sorry, here's negative 3, and I go to positive 3 here, if I exclude those points, right, if I just ignore what's happening at 3 and negative 3, everywhere over here it's continuous, everywhere in between it's continuous, and everywhere over here it's continuous. It's just at the places that you can't plug in that value of x, the implied domain, that you would have a problem. And that's what that theorem is saying. All rational functions are continuous on their implied domains. All trig functions, sine, cosine, tangent, secant, cosecant, cotangent, all of those are continuous on their implied domains. So we've already seen sine and cosine, they're continuous everywhere. Tangent had problems, didn't it? But it only had problems where you have division by 0. And then all exponential and log functions are continuous on their implied domains. So again, as long as you're working where the function is defined, the graph that you're drawing can be drawn without picking up your pencil. There's no holes in it, no jumps, no breaks. So we can put those away, put those in our memory that anytime we see any of those functions, they are continuous. Here is an example. There's a polynomial function. You can see that that polynomial function is continuous everywhere, right? Here's a rational function. I just showed you something like that. Continuous on its implied domain. There's a sine function, continuous. Oops. There's an exponential function, e to the x, it's continuous. A logarithmic function, there you go, it's continuous. Now the last thing with continuous has to do with composition. So we've already talked about if you take two continuous functions, add or subtract them, it stays continuous, right? Take two continuous functions, multiply them, stays continuous. Divide them, it stays continuous so long as the denominator is not 0. But what about if you do composition? That means you take a continuous function and you plug it into another continuous function. So the first example I have here, and it's hard to see it over there, so I'll write it down here. I'm looking at this function sine of x squared minus x. So I'm plugging a function into a function, right? The function that's getting plugged in is this, right? That is a polynomial function. It is continuous where? Polynomial functions are continuous everywhere, right? So that's continuous everywhere. I'm plugging that into a function sine that is also continuous everywhere. So the graph of this should be continuous everywhere. And that's the graph of it right here. This is the graph of sine of x squared minus x. And you can see by looking at it, it's nice and, you know, no picking up pencil, no breaks. What about this one? E to the cosine x. So which function's being plugged into which one when I write that down? Is e being plugged into cosine or is cosine being plugged into e? Cosine's being plugged into e. So the cosine function is continuous, right? And e to the x, right, the exponential function, is continuous also everywhere. So if I graph this function, I should expect to see a continuous function. There it is. That's e to the cosine x. Nice continuous function. Now, what about the next one? Natural log of x over x squared plus 1. this right here, right, is continuous. If I ignore natural log, that's continuous, except where the denominator is 0, right? Which never happens because you can't make the denominator 0. It's impossible unless you use imaginary numbers. So x squared plus 1 can never be 0. So I don't have any problems with the domain of this. Do you all agree? So that I plug in, I get values that come out. Now, natural log is not continuous everywhere because it has a domain. When you have a natural log, you can only plug in positive numbers. You can't plug in 0 and you can't plug in negatives. So if this thing ever is negative, or if this thing is ever 0, then this thing doesn't know what to do, right? But I do have a graph. Let's see what it looks like. There it is. Okay? And you'll notice that it can be drawn without picking up my pencil on its implied domain. Over here, there is no graph because you can't plug in 0, you can't plug in negative numbers, right? And then I can keep going. There's more, like this one right here. That's an interesting looking function. That's the square root of x squared plus x minus 2. Inside the root is a polynomial, which is continuous everywhere, right? The root function is continuous on its implied domain, but there are some domain problems here. Like you can't plug 0 in for this, right? Plug in 0 here, you get a negative. Root of a negative can't do. So there are certain numbers we cannot plug into this. And you can see from the picture, here's the group of numbers you can't plug in, anything in here. But if you go outside and outside, we have graph. And guess what? That graph is continuous. All this is really doing is guaranteeing you that the picture you get is not going to do some crazy shit and start jumping and breaking and having holes in it. That's all this is guaranteeing you. Now, it leads us to one of the most important theorems in this class, and it's something you've been using for a long time that you kind of didn't realize you were using, and that is what's called the intermediate value theorem. IVT is another name for it. Let me try and explain the intermediate value theorem to you. And then I'll go back and read it to you, all right? Let's see here. Let me try this with a different example before I show you that picture. All right. Let's say that I have a function here. And here's all I'm going to tell you, is that at A, I have this point, okay? So f of A is defined. Agree? Yes. I'm also going to tell you that f of B is defined. And I'm going to tell you that, let's say this is the value 10, and let's say this is the value 2. So we all agree that f of A is 2, and f of B is 10. Yes? Just from that picture. Now, let me ask you something. Is it possible, I need to draw the whole function. I've only given you 2 points here. But let me tell you that there is a function, okay, that goes from here to here. I haven't drawn it. Just imagine it in your own mind, the function that goes between here and here. Does that function ever hit, I don't know, somebody give me a number between 2 and 10. 5? Okay, so 5. Does that function that I need to draw, does it hit 5 ever? What do y'all think? Let's take a vote. I'm telling you that there is a function that goes from A to B. Like there's no holes, okay? There's no holes. It's defined all the way in between. Am I guaranteed that I have to eventually hit 5? So how many of you think I do? Okay? Anyone think I don't? No? No? You don't? Just, are you being skeptical? Okay, here we go. Watch. I said that I have to draw a function between here and here, right? And that at every point it's defined. Is that a function? Does it pass the vertical line test? Okay, is it defined at every point? Yes, 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 yes. What about here? Yes, no, there's a solid dot there. It's defined, right? Yes, 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 all the way to the end. I have a function that is defined all the way through here, right? Does it ever hit 5? No, it never hits 5, right? There's no x value I could plug in that gets me to 5, right? It's like I jumped over it, didn't I? Right. Because I told you I was going to draw a function between here, right? So you assumed I was going to somehow connect that dot to that dot, right? And you assumed that. So you assumed it was continuous, didn't you? All right? The intermediate value theorem says that if it is continuous, right? So now let me rephrase the question. Start here. And now I say to you, I'm going to connect this to that with a continuous function. Is it guaranteed that I'm going to have to hit 5 somewhere? If it's continuous. Yes, absolutely. There's no way to not hit 5. If I can't pick up my pencil and I've got to get from here to here, I've got to hit 5 somewhere, right? It's impossible for me to not. So I can try and avoid 5, but I got to get to here, right? So, okay, I have no choice. There we go. I went through, right? Now, what if I try and be sneaky and leave a hole there and say, I got you. Well, that's not continuous, right? You've got a removable discontinuity there. So that's not a continuous function. So let me now go back and show you the intermediate value theorem. And maybe it'll make a little more sense now that I've put that up there. So the intermediate value theorem says this. This is going to look real mathy, okay? Suppose you have a function, and it's continuous on a closed interval AB, where f of A does not equal f of B. That means that we have, at A, we have some value, and at B, we have some other value, all right? So these 2 points are not the same height. Then it says, let n be any number between f of A and f of B. So this was like me asking you to pick a number between 2 and 10. So let n be any number you want between the 2 outputs, between that height and that height. Pick an n somewhere in there. Then this theorem says there must exist some number c in this interval. So there's some number in here, something in here between A and B. There must be a number where when we plug c into the function, we're going to get n. Does that make more sense now that I've shown you that picture? I hope it does. So here it is. We have a function, right? It's defined on a closed interval, so let's cut it off. Okay? Now, let's look at the values. Here it's -12, here it's 13, right? Now, choose any number you want between those 2. Okay? Now, I guarantee you that I can find the x. See, I know that if you pick that number n, it's going to hit the graph somewhere, and that's going to correspond to some c value in here. So the intermediate value theorem guarantees you the existence of some number in that interval that will basically generate any number in between. So if I start sliding this number around, notice that, of course, my c value is going to change, right? So there we go. But we must have that. If that's not there, I gave you an example that didn't work, right? Okay. Now I said you've been using this, but you don't realize you have been using this. So let me give you an example of this, and this may look crazy to you. This all depends on your college algebra background. Okay, so in a college algebra class, you should have been asked to graph a polynomial like that. So you were being asked to graph this. And to graph this, what you would first do is you'd look at the power, you'd look at the leading coefficient, and that would give you your left and right behavior. And there was a little table that maybe you memorized or you were allowed to have in class. We would have known from just this number and the fact that that's a 1, that the left side of this polynomial goes down, the right side goes up, and in the middle you kind of have to work it out. Hopefully this looks familiar. If not, just try and follow along. The next thing you would do is you would actually take this and factor it. So if I factor out an x, I get this. Y'all agree? Right. And then I can factor that even further because this is a trinomial that factors x minus 5x plus 1. And then what you would do is you would set each of these equal to 0, and those would give you the 3 x-intercepts of the polynomial. So if I set those to 0, I get x is 0, x is 5, and x is negative 1. And then you would know this. If you graphed this, 0, 5, negative 1, you know you have x-intercepts. And you know your left side, your right side goes up and your left side goes down. Okay, and that it has to hit those 3 points. Does anybody know, or remember what the next step would be to graph this? See, this all depends on the way you were taught, but yeah?
Don't you pick a point?
Yeah, you pick a point. You pick a test point. So I would pick a point like in here. Let's say I picked the number 2, okay? And then what I would do is I would plug that into the function and see if I get positive or negative. So let's say I plug 2 in here. Let's see what happens. 2 here we would get 8 minus 2 here we get 4, so 4 times 4 minus 16, and then minus 5 times 2 would give me 10, yes? And that would give me a negative number, right?
Yes.
And that means that my graph is down here somewhere. And then what you could do at this point is you could conclude that this thing goes like that and like that. And the reason why you could conclude that is the intermediate value theorem. Because look, if you are going to go from this point to this point, right? And you have to be down here, it's impossible for this graph to ever come up here. Why can't this graph ever come back up here? I would have to have another x-intercept, right? It would be, for me to go from 0, right, that's how high it is, to 0, to go from 0 to 0, if I'm down here at a negative number, it's impossible for me to go up to a positive number and then back down to 0. Because then I would have had to have gone through 0. Why do I have to go through 0 to get to here? Why would I have to go from here to here? Why do I have to go to 0? Because it's continuous, right? It's a polynomial, it's continuous. So you're guaranteed that there's not going to be a jump and that you magically appear on the other side, okay? So you use this, you don't realize you're using it, but doing this little test point is all a result of the fact that this is a continuous function and the intermediate value theorem holds. All right. If this section seems real, I don't know, like less mechanical, like we're not doing a lot of like mechanical math right now, right? We're doing just a lot of ideas. There's a few sections in the class that are like this, where it's a lot of thinking as opposed to mechanics, but we are going to do some problems here. We're just kind of leading up to it. All right, there's our intermediate value theorem. So just look at that. Does the intermediate value theorem apply here to this function? It does not, right? It's not continuous. So we could restrict it on a closed interval. We could find the points there, and then we could try and pick a number in here. But just like I showed you before, in here, see how it turns red? That's, nope, you can't ever get to that value because there's a jump. Now, y'all all right? I heard a big sigh. Okay, let's read this. Use the intermediate value theorem to show that this equation has a solution somewhere in between 0 and 1. Okay, so let's all look at that equation. Cosine of x equals, cosine of x equals x. What's being asked is for us to show, somehow prove, that a solution to this exists, and that the solution is somewhere between 0 and 1. It is not asking for me to find the solution. Do you all understand that? It's not saying find the solution. It's saying show me that a solution exists in that interval. And I'm going to use the intermediate value theorem to do it. Now I should point out that that equation is impossible to solve by hand, right? You can't solve that by hand. There's no way to do it. You can throw every single thing you've ever learned at this equation, and there's nothing you're ever going to be able to do to get x by itself equals a number. Can't be done, right? You can't say you know what x is right now, because to know what x is, you'd have to know what x is, right? So what number do I plug in here to make it true? Well, the intermediate value theorem is going to allow me to show that a solution does exist, so that at least we'll know, yes, an answer exists out there. Finding it, I said it can't be done by hand. It can be done numerically, which means we can use a computer to find that solution, and we will do that later on in this class. We'll be using something called Newton's method to be able to find the solution of that. But it requires an algorithm that you would feed into a computer, and the computer would run the algorithm over and over and over, and then eventually it would just kind of narrow the answer down. But that's further down the road, okay? So how do I show that this has a solution? All right. I need to show this has a solution somewhere between 0 and 1. Somewhere in here, the answer to that exists. So watch how I do this. This is actually very clever. It's not me. I'm not saying I'm clever. Someone showed this to me, and now I'm showing it to you, and it's pretty clever. So how about I do this first, and just agree with me or disagree with me that that algebraically is okay to do. Is that okay?
Yeah.
All right. Now, I'd like for you to consider something. Just look at the left-hand side of this. And I'd like to actually call the left-hand side of that the function cosine x minus x. All right? So let's now back up. Let's say I just came here, just ignore all this right here, and I said, hey, everyone, take a look at that function. See that function right there?
Yeah.
First thing I'm going to ask you is it continuous? Is that a continuous function?
Yes.
Yeah, cosine's continuous, right? X is a polynomial, it's continuous, and when you subtract two continuous functions, it's continuous. So this is a continuous function. If I graph it, it's, right? No picking up of the pencil. Now I want to show you something else. I want to ask you what f of 0 would be. So what's f of 0? So that's cosine of 0, right? Minus 0. And what's cosine of 0? 1. 1 minus 0 is 1. So when I plug 0 into this function, I get 1, right? Now, let's plug 1 in. Notice I'm using these 2 points. 0, now I'm going to plug in 1. So what happens when I plug 1 in? See, I get cosine of 1 minus 1. And now I need somebody on their calculator to do cosine of 1. But do you really need to do it? I guess, yeah, let's do it. And then I'll tell you what I was thinking. Make sure you are in what mode on your calculator if you're going to do cosine of 1. What mode? Radian or degree? Radian. Because if there's no degree symbol here, it's understood to be radians. So somebody in radians do cosine of 1, and then subtract 1 from it and tell me what you get. Go ahead. Go out on the limb, Brian. What? You did cosine 1 and then took away 1? Let me see. Oh, no. Okay, so you close your parentheses after the 1 in the cosine. Because what you did was cosine of 0. Does that make sense?
Yeah.
Okay.
Negative 0.459.
Sounds right. That okay? Now, I claim that I'm done now. Why am I done? Why have I shown the solution to that equation exists between 0 and 1?
What was the question again?
Why am I done? The original question was for us to show that a solution to this exists somewhere between 0 and 1. And what I did is I said, okay, move everything over to one side, and then call that a function, and then plug in the two endpoints, 0 and 1, and you get these two answers. Why am I done showing what I needed to show? Yes, these aren't the same, but there's something more important about them not being the same. Like if this was 3 and this was 2, that wouldn't be enough. So one of them's positive and one of them is negative. So let me look at it this way, or let me have you look at it this way. This is a function, isn't it? And it has a graph. And when I draw it, I don't get to pick up my pencil. And when I plug 0 into that function, what do I get? 1. Right? And when I plug 1 into that function, what do I get? Negative 0.49? Somewhere over here, right? Do you agree? And if this is a continuous function, I have to be able to draw from that dot to that dot without picking up my pencil. Which means to go from a positive number to a negative number, I must pass through what? 0, right? So I've got to go through 0 here, right? Somewhere. Somewhere between 0 and 1, I have to pass through 0 on the y coordinate. Which means that somewhere between 0 and 1, this function has an x-intercept. And having an x-intercept corresponds to setting the function equal to 0, doesn't it? That's how we find x-intercepts. And setting the function equal to 0 is equivalent to solving that equation. Does that make sense? Now, have I found the number? Have I actually found the number? No. I don't know what it is. I have no idea what it is. But I know it's between 0 and 1, right? Make sense? So now, how could I get a better idea of where it is? Well, how about we do this? How about we cut this interval in half and go to 1/2? Yes?
So on the original question, did it say, are you assuming it's already continuous, or?
No, it never assumed it was continuous.
Oh, it never assumed it was
And it just said, show that this equation has a solution between 0 and 1. I took the equation, moved everything to one side, and then I looked at the left side as a function. I determined that function is continuous. I checked the value of the function at the two endpoints. Notice that one was positive, one was negative. If I ever have a change in sign, I've got to go through 0. So I've got to go through 0 between 0 and 1. Right? That's enough for me to say that has a solution. Now, someone on their calculator, I would like for you to do f of 1/2. So what's cosine of 1/2 minus 1/2? And make sure that half goes into the cosine. Somebody give me an answer there. 0.377? Say it again. 0.37. Good enough. Okay? So look at this. At 1/2, right? When I plug 1/2 into the function, it's spitting out a positive number, isn't it? Which means I'm up here. I just happened to draw the graph right, okay? Do you see I'm up there? Which means the solution is actually between where and where? Where's the solution? Between 1/2 and 1, right? Because it's between 1/2 and 1 that we have a change in sign, don't we? So how could I get even better? Go a quarter of the way here, right? So how about that's 3/4, isn't it? Because this is a half, that would be 3/4. Let's do 3/4. That's a 3/4. So cosine of 3/4 minus 3/4. What do you get there? What'd you get? Negative 0.01, something like that? Okay, so I did a new graph over here because I think we need to kind of put all this information together. At 0, we were at 1, right? So we were up here. And at 1, we were negative, so we were down here. So we knew that somewhere we had to go through, right? At 1/2, we turned out to be positive, so we're here, right? And at 3/4, we turn out to be negatives, which means we're down here somewhere, right? So I know now the solution is between where? 1/2 and 3/4. So what I could do is cut that in half and take that and go in there and try it again. And what I'm doing is I'm actually narrowing down where the solution is, right? Wouldn't it be nice to maybe write a little quick program to do this for me? It would be a pretty short little program I could write that would just keep testing whether or not I'm getting the sign change. And what I would do is I would start narrowing down this thing into a smaller and smaller interval, right? And a computer could do that thousands and thousands of times in a blink of an eye. And imagine that interval keeps getting cut in half, right? Half, 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 half. And eventually, isn't that like just infinitesimally small? So that's exactly what's going on when you go to a website like Wolfram Alpha. Oops. You go to a website like Wolfram Alpha and you type in here solve cosine x equals x. I should probably type the whole thing in, huh? Cosine x equals x. And I have it solve it. It's going to sit here and it's going to give me an answer of 0.739, right? The way the computer is doing this is, see, we know right now, just by looking, we know it's between 1/2 and like 0.5 and 0.75, right? Turns out it's 0.73908. This right here is an approximation. See the little squiggly equals? That's an approximation. What the computer has done is it has done this thing and it's narrowed it down, and it's in the program. It says once the distance between those two endpoints, once this distance is like 0.00000, maybe like 10 zeros and a 1. When that distance is that small, just give me the number right in the middle. So it's just averaging. So like if we wanted to stop right now, we could guess that the solution is right in the middle of those. Does that make sense? That'd be a terrible guess. But if you do this thousands of times, then it's so narrow that your guess is as good as the answer. It's approximately good enough. Does that make sense? This is actually called the bisection method. And in a computer class, math majors who have to learn how to program computers, they have to implement this method. They have to do it and code it up and stuff. Okay, but it all relies on what? Continuity and the intermediate value theorem. You have to have those two things in order to be able to do something like this. I feel like maybe I'm more fascinated by this than you are. It's okay. We continue. Now I'm going to put something up here. It's going to look really weird. Well, I need that out of my way for a second. I'd like for us to consider the following piecewise function. And I'm going to put a star next to this because we're about to be done with the section. And this problem right here is what you should expect to see on a test or a quiz. All right? A problem like this. Hold on, I need to look at something before I finish that. Yeah. All right. This is what we call a piecewise function. Does it look pretty nasty? Yeah, it looks weird, right? This piecewise function is made up of three functions. The first piece of this function is a rational function, right? And it's only this rational function to the left of 2. So if I'm drawing this, here's 2. If I imagine just this imaginary line through 2, to the left of this, it's this, right? Then, between 2 and 3,